Makes sense.
Back, welcome back. Second lecture by Hayden.
Thanks for that. Okay, morning. Today we're going to pick back up with where we were yesterday, although we're going to start to get much more specific, much more quickly. But before we do that, I just want to mention a quick aside, which maybe I'll put over here on the right to distinguish it from the rest of the rest of the lecture. Last time I meant to say one other very useful fact about these homology theories that we're talking about, in particular top-floor homology and bottom homology, is that they satisfy duality isomorphism. So this was sort of put on an updated version of the first set of exercises, but that was before, and that was after it went to press. So I just want to sort of briefly state it. You can see the exercises for a more precise statement. But the point is that if I have the mirror of a link, so here I'm thinking about reversing all crossings in place, then there's going to be an isomorphism between that and at the chain level, the dual complex to the chain complex for the original. And it's respected by the coordinate maps. So in particular, if we have sigma, let's see, how do I want to write this? We go C, let me just make the same notation I had before. Okay. So if I have, normally sigma would be, if I ignore the negative, giving me some map going down to chain complex source L1, but we're working with the duals. And so in this case, we go from mirror down here. So this is going to be C of negative sigma, where what I mean by negative sigma, if we're given sigma from L0 to L1, then negative sigma goes from L1 to L0, and you mirror each frame and run the movie in reverse. So we'd like to understand the relationship between the coordinate map induced by that and the original map sigma. And the point is that under this isomorphism up here, we're naturally getting the, I want to say this, I guess we'll put, it's a lot of parentheses. So we're looking at the dual map between the dual complexes. Okay. Okay, so I won't say too much about that, just wanted to mention that as one of the important formal properties. I encourage you as an unofficial exercise to try to, after we sort of discuss what we need to today, to try to prove this. That's sort of unofficial exercise. All right. And so I'm going to be unprofessional and probably hold my tablet as a sort of a security blanket for a bunch of this because I don't want to get any details wrong. So today we're going to start by being more precise. All right, so let's go ahead and recall where we were. In our basic sketch of the setup of Kavan homology. And I should clarify, as I said today, we'll focus on the Cobordes maps in Kavan homology. And so we'll need to request more details about the setup. What we had was a sort of thing that was doing all smoothings of our link diagram. And then we said to get their labels, we're going to take our coefficient ring, R, and promote it to this thing, A, which is going to be R join X mod X squared. And so it's really just generated over R by 1 and X. And right now, this is just an R module, but we're going to end up giving it a structure of a Frobenius algebra. That'll be an important step. But to get there, I want to make a declaration that today, unless I specify otherwise, as it says up there, we're going to take R to be Z2, so we don't have to worry about signs. Here and there, I'll try to make a word, or say a word about what happens if you try to work over the integers. And I might write Z mod 2, I might write F2. I can't stay consistent. Okay. So last we checked, one of the things we had done was assign these labels in A to components of smoothings of our diagram, right? So maybe we had something like this. Maybe we had like a 1, an X, a 1, who knows? And what we want to think about is these living in a tensor power of A. So the smoothing with n components, assign A tensor with itself n times. Okay. And so that's going to do the job of populating all of our possible combinations of labels. And now we said that the arrows in the complex are going to involve changing 0 resolutions to 1 resolutions. So they're outgoing or increasing edges in the cube of resolutions. And so what we need is some maps here. That's why. So what we want, if we have a link cobordism, if that's initially giving me a sort of a morphism, if we want between link diagrams, we want to think what's that supposed to do with the level of labeled smoothings. So we want some link cobordism to give us some cobordism map. And so to do that, what we need is to know what is it going to do to labeled smoothings. So we're going to roughly follow Barnaton's O5 paper here in a sort of a limited scope view of it. So we're going to start abstractly. So what's that going to mean for us? The setup we want to consider is D2 and some collection of circles in it. Now in the sort of the full setup, we would also allow arcs with boundary on the boundary of this disk. But for now, to keep things simple, we're going to imagine that sort of the entire picture of our smoothing is visible inside of this disk. And we'll let sigma be a closed one manifold embedded inside of D2. Okay. So we're thinking about this as being a stand-in for a smoothing. So what we want to think about is what should we do with a embedded cobordism? Start. So let's say we're given some embedded cobordism in this more limited little world. So S, let's say it goes between one such sigma and another such sigma. So maybe I got 2 up here, maybe I got 3 down here. Here's S inside there. And I'm going to think about this as, let me get some other chalk. Yikes. Right. I'm going to think about this as going up in D2 cross the interval. So I believe this is opposite, if I remember correctly, of Barton's conventions. I sort of, today will always try to indicate whether I'm reading things up or down as instead of just sort of setting one sort of standard. I mean, in an ideal world, I really want to do left to right, but for some bizarre reason that I can't quite figure out, my brain will just not draw things correctly going laterally. It sort of can't see behind things or something. Okay, so down here's the 0 level, up here's the 1 level. And we haven't even considered the labels yet, but if we set number sigma I to be the number of components in sigma I, then we know that our recipe for the Kawano machine is to assign A to the number of components of sigma I to sigma I. And now what we want to do is associate some map to this cobordism that goes between these powers. So we want something to go from A to the number of components in the bottom smoothing to A and the number of components in the top smoothing. Okay. So before we go further, I want to pause and ask if there's any questions about the setup or anything else. So the idea here is this just like a no-go zone to well, any such S decomposes, I'll say up to isotopy boundary into births, saddles, deaths, and the trace of isotopy. In this case, it's going to be planar isotopy because we're still in our sort of cartoon world instead of the real world. Okay, so just to illustrate that here, we start with these, this trace of isotopy up until you get to here. And here we've changed the topology of the level set. We've had a saddle that joined these two components. And then we have another saddle that splits this component. And then more saddle. So in here we haven't happened to draw any births or deaths, but maybe just to include such a thing, you could always maybe look at something like this. And so our first step is to assign maps to these elementary bits. And so that's, I'm gonna walk through it, but that's what's up here. So I took the liberty of starting out by copying this down, just to avoid sitting there sort of mechanically copying it down as we watch me do that. But let's talk through it. So what I'm going to do for each of these three types of critical points that we could be passing, I'm going to have sort of a local model. So here, this might just be a little neighborhood, for example, of a saddle point. So maybe you should think of this as living inside of some, this is a smaller subdisk times an interval. What we're going to do is define maps according to the labels. So for example, here we have a map going from strands or arcs arranged this way to arcs arranged with the same endpoints but opposite connectivity. And two things could happen. If we zoomed out, these are supposed to live inside of some sigma, some closed one manifold. So you have two cases. Either these go down here, either these were part of the same component, in which case this is going to split it into two components, or so if they were part of two different, sorry, they're part of the same component. Then I'm drawing an arc in for where the sort of pinching is going to come together to form a saddle. Part of the same component, we'll get them splitting into two components. If they're part of two different components, they're going to become one component. And so that means we have to either consider what happens to one label splitting into two components with their own labels versus two different labels combining. So in the case of combining, the map is essentially just multiplication in, I guess we didn't give it a name. Well, yes, I guess we did. In A tensor A to A, right? So this M should be a map from two copies of A to A, or in general, N minus or N copies of A to N minus 1 copies of A, because there might be other components involved. And so this just should look naturally like, 1 times 1 is 1, X times X is, whoops, that's weird. Testing you. Actually, later we will have to consider that case. But right, X times X is 0. 1 times X and X times 1 are X. And then in the split case, we'll define it to be 1 goes to 1 tensor X and X plus X tensor 1. And then X just splits to X tensor X. Okay. We could also pass a local minimum, and there we have a birth. And so just like we said these should be a map from A tensor N to A tensor N minus 1. Or sort of more narrowly here, really, A tensor A to A. Here we said A to A tensor A. What should happen at a birth? Well, we should think about the algebraic object being assigned to the empty set as being the coefficient ring. So this should be a map from our ring to A, or more generally, from our ring tensor a bunch of copies of A to A tensor a bunch of copies of A, because again, we have multiple smoothing components. But R tensor a bunch of copies of A is just that bunch of copies of A. You just absorb R in. So what do we want to do? We want to send, I should have said at the beginning, R is going to be a commutative ring with identity. And we're just going to map that to the identity element in A. Okay. So viewed as an element of A. So it might seem sort of like we're not saying anything, but I do want to distinguish between here, this one, we're thinking about this as sort of being a coefficient. It's in our, if we're viewing A as an R module, this is the coefficient 1, whereas this is the element 1 in the R module A. Okay. Okay. And so what does that mean in terms of the labels? Well, I guess let's look at depth real quick. And finally, the final move is tapping off a component. And if the label is 1, send it to 0. If it's X, we'll send it to a 1. And again, this is 0 in the ring. This is 1 in the ring, not in the not in A. So we should think about that as saying, for example, if I was passing this, then this would now receive a 1 label on it. Okay. So we'll do some more examples. So I'm not going to corrupt this sort of table with a label at the moment. So are there any questions about these definitions before we put them to work?
If you're working over Z, then in the split, do you have a sign?
So in the split, no, although I'm suddenly talking about where the signs do go, but no, I can't remember where that was asked from. Over here, yeah. Answer is no, which we sort of think as coming from the sort of intrinsic symmetry of the move itself there. Okay. But for these, there won't be any signs. Once we work with certain deformations of the underlying sort of, well, maybe I should have introduced the word. I want to say this here. So to finish answering your question, let me just add a word in. What we're doing we're promoting the R module to a Frobenius algebra or a Frobenius system or Frobenius something or other algebra with these operations. So epsilon, m, delta, epsilon, and iota. And for other choices of Frobenius algebras, we might have some signs involved. Yeah, thanks. Yeah, good question. Yeah, any other questions as we proceed? Okay. So we're surprisingly close to calculating cobordism maps and homology already. Regardless of whether it's apparent or not from here. But again, as a sort of a toy model case, let's go ahead and that'll be too many steps. Let's do an example. Okay, so let's say this is our cobordism. Say it's going upwards. And let's say we start with the labels. What do I want? How about 1, X, and X? And I want to understand where should they go under this cobordism or the map associated to it. So what I'm going to do is start down here. Over on the right, we have those 3 components. When we get to here, we're going to have 2 components. When we get to here, have 1 component. And then up top, oops, yeah, I guess that's fine. We have 2 components again. And so we want to understand what happens to the labels. And so we can just practice using these. So we start with 1, X, X. The first thing that we see is use this space over here. From here to here, we see a death. And then, so what that's going to do, that's going to send this x to kill this circle and send it to 1. And so we just have this 1 and this x remaining. Okay, next we have going from here to here with a saddle, but what's the particular to a saddle? It's going to be a merge. And so 1 times x, that's going to go to x. And then from here to the top, what do we see? We see a birth. That's iota. And so this x just goes to there, and we witness the birth of a beautiful baby, one labeled circle. Congratulations. Okay. Okay, so there are questions about this toy case of, we're not looking at some four-dimensional surface embedded in 4 space yet. We're looking at some cobordism embedded in 3 space, D2 across the interval. But are there any questions about that model calculation?
If the circle that died was labeled with a 0 instead of an X, would that kill the whole thing?
Okay, so yeah, so the answer directly is yes, because if it was truly a 0, then when we think about these labels, we're really living in like a tensor product.
Sorry, I meant to say 1.
Yeah. So no, yeah. So let me address both things with both versions of our good questions. So if it was a 0, I want to point out that would kill the entire thing, and that means that the entire map now is going to die. It's not just like that component dies, right? Because that's saying that I'm going to send it to 1 tensor x times 0, whereas because we sent x to 1 under this cat map, it was 1 times 1 tensor x. Okay. Now, what if it was a 1 label? Now there, what we're thinking 1 in the algebra A, and right. So since epsilon of 1 is 0, then that would kill. You would now get 0 times this 1 tensor x. Yeah, great. Yeah, other questions about this?
In this example, the tensor at the bottom and the tensor at the top, they're like simple, like you just have 1 tensor x, tensor x.
Yeah, that's right.
But if you have like a split, it could be like a sum.
That's right, exactly. So then, just to, yeah. So if this was where, I guess I don't have any. Right, but that's right. So then it would look like this plus some different labels on the same underlying smoothing. Great. Now, by construction, I also want to point out we have the composition property that we want, where we want actual 4D cobordism maps, or 2 dimensions inside of 4D to satisfy. That is, if I cut this somewhere, the map is the composition of them. I'm not going to write the following thing on the board, but let's say I wanted to compose formally the sum of 2 cobordisms, because we want to be able to do that. Then you're going to do it in sort of the only way that is sort of naturally distributive, which is that if I had this thing plus 2 other ones emanating from here, that composition is this plus this composed with one of them plus that composed with the other one. Because even though we might not naturally think about adding cobordisms, certainly we could think about adding elements down here, etc. And we will sort of want to be able to think about adding cobordisms themselves in certain contexts. Okay, so another remark real quick. I should have put this with here. Actually, I will. No, sorry, wrote the blue. So I should say other Frobenius algebras give other homology theories. So we'll consider some of those tomorrow. Okay. So yeah, any other questions about this before we put it to work with the actual Kavanaugh complex? Yeah.
So if you add a kind of a trivial sphere on the side of your And everything just vanishes.
Yeah, great. So from here, we can already start to observe certain things. So if I have sort of anything over here and then closed sphere, then right, what we're going to see is the birth of a one labeled circle, and then it's going to go to 0. So the sphere is always going to induce 0, for example. And from here, we'll do in a moment, you could also see that a little torus is going to induce multiplication by 2 on R. So we're starting to see the shape of what was promised by the sort of formal properties discussed yesterday. Okay, so with this in hand, what we're going to do now is just quickly see why this helps us define what the actual differential is on the quantum chain complex and what the borders and maps are. So this definition is going to make it apparent that much like everybody in this room, quantum homology was born to study surfaces. Okay. So in the cube of resolutions, we want to consider, we said, all the oriented edges. So every directed edge that goes from a 0 resolution to a 1 resolution. That's going to correspond to either, well, it's going to correspond to some saddle, and that's going to either be a merge or a split. I'll say it corresponds to a saddle. So we apply M or delta as appropriate. Okay. Then sum over the outgoing edges. So let's just do a simple example just to clarify what the definition or what that claim. Let's see if we can drop any more jam. To see what that looks like in practice. So let's say we're looking at some labeled smoothing, which is, we'll go like this. So I'm going to do something that it's not really official notation, but I find it useful, which is that sometimes I like to put in sort of the ghost of a arc. I don't mean these as arcs denoting saddles. I mean, they will be in certain cases, but really the stand-in for this being a 0, and a 1. Those, again, those are not labels in A, those are just telling us how these were resolved. And so the outgoing edges, there's not an outgoing edge from 1, because we can't turn that from a 0 resolution to a 1 resolution, but you can for these. And so the boundary of alpha is going to be a sum and again, I'm working over Z mod 2, so I don't have to worry about signs. In particular, you might notice that the enumeration of crossings is not factoring in here. If we're working over Z, we would have to do a term to the coefficient. So we're going to change first this 0. Oh, sorry, I didn't give this a label. Let's make this thing labeled 1. So it's 1 in A. So we could change this 0 resolution to a 1 resolution. And so what's going to happen? Oh, whoops, I'm going to do, is this what I meant to do? Okay, well, okay, we made our bed, align it. I'm just gonna copy this down and then start speaking again. Okay, so ignore this for a second. Here, this was a 1 label, and we're gonna split. So it's gonna go to a 1 and an X and a 1. And then we also have an arrow coming out of this. And so we leave this one on the left, 0. But now we resolve this crossing. And again, this is a split. So we get 1x and x1. So the boundary of alpha is this sum of labeled smoothings. Okay. Any questions about that example of applying the boundary map to labeled smoothing over Z2? Okay. So now let's move to the setting we really want to think about. As a stepping stone, let's think about elementary linked cobordisms. And I'll call these Morse cobordisms. So for births, deaths, saddles, and saddles, we should say in a link cobordism, we want to apply iota, epsilon, m, and delta locally for labeled smoothings. So let me shift back over there to the left, and let's do example of a standard linked embedded torus. So the picture we're going to draw is going to be sort of have its feet in 2 different worlds. We can interpret it literally back in the D2 cross interval world or in S3 or R3 times interval. So let's look at a standard torus. You hear me thinking about this as going upwards. And so I start down here with the empty set, and I'm going up here to the empty set. And the first thing I see is I pass a local minimum. And so at the chain level, that's going to go from the element 1 in the ring R to, I guess I'll write it in blue since that's the color of the cross section, to, well, what should it be? If we have a birth, it should be a 1 label. And then if we pass this, so that's iota, if we pass from here to here, that's going to be now a split. And so this is going to go to the sum of 1 and x plus x and 1. And then we're going to merge. And so 1 tensor x, we go to x, 1 x tensor 1, that's going to go to x. And so this is equal to 2x. I want to notice I'm moving this 2 outside here. Oh, I should have said this. Let's do this over Z. Elements of the ring, the underlying coefficient ring, we're allowed to sort of move freely around between components because the labels and components live in a tensor product of A. However, X cannot move freely around because that's not part of the underlying coefficient ring as part of the algebra A. So I'm allowed to pull the 2 out and to say I'm multiplying this by 2, or I can put the 2 inside there if I want. But let's just point this out. Okay, great. So we have 2x, and then we have depth, and so this is just going to map to 2 times epsilon of x, which is 1, so just to 2 again, and that's in R. Okay, and so we're seeing here that this is multiplication by 2 in the ring, which is essentially what we claimed we wanted it to be for any closed torus. This is at least showing for the standard one. Okay. So quickly, what I wanted to do is Reidemeister moves. So here we had very boring link diagrams. If we want to think intermediate, we could say, like, what if I do a saddle, let's say like right here. I do like a pinch right here. Then on this smoothing, what should that do? That should apply a saddle right here. And the calculation of what that does is going to be similar to how we did it for crossing changes. You would do a split map. The question is, what do we do with Reidemeister moves? So those, what we want to do is say, unlike an elementary cobordism, there's not some immediately obvious cobordism in D2 cross the interval associated to a Reidemeister move, but we can choose one. So we're going to assign R1, R2, and R3 local cobordisms between smoothings in the D2 follows the diagrams universe that sort of it's being projected to and smooth times the interval. So let's see, do I want to put this? I think I want to put this up here. So I'm just going to write down a few of the Reidemeister moves, and goodness, this normal. Do I proceed? No.
It doesn't go very far.
Oh man.
You can pull it as far as you want.
My PhD advisor is John Baldwin, very, very strong. So I feel like I'm, always insecure. I need to like muscle up in front of the audience. So this would be nothing for John. He'd already be whole whiteboard covered. All right, so let's do this here then. For R1, let's start with the simplest case. That's probably kind of hard to see. So this is going to be a little local rectangle. And let's say I'm considering this. So I'm untwisting that. Is this visible? Okay. So here's what it looks like in the diagram. And we're going to write down for each smoothing that we could consider, we're going to consider what the induced map is. This thing hates headers. Oh man. Okay. Hopefully that's legible enough. So one of the smoothings we need to consider is smoothing this into a 0 resolution here at this crossing. And so what are we going to do here? Well, I'm going to start to use some ornaments the point is that the smoothing is itself now at least if you zoom out, some simple closed curves, or in this case arcs as well. And so we can just directly define some cobordism in V2 cross I. What is it going to be? It's just going to be the cap cobordism. Okay, so I'll put a sort of legend over here on the side. So this will be epsilon for depth. If you see a little shining opposite arcs going out, that's iota for a birth. And then we'll use either this or this for saddles. And then we're going to have one more ornament we'll need in a moment, but let me just finish stating a couple things right here so we can wrap up with one calculation before we go. So on this smoothing, it'll just apply this. On the other hand, if you have the one smoothing, it's going to just kill it. So that's not a cobordism, but we can think about that as some, if we're thinking about trying to turn this into an outbreak object, this is a legitimate morphism between the sort of natural category that we're going to turn these little diagrams into. If I want to consider its inverse, that's going to go from here to here. And now there's only one smoothing to consider because there's no crossings. And we're going to write the definition down in two different ways. Okay. Actually, maybe I'll just write it down just this way. So here we see like a little maybe turtle that just hatched trying to get to the water before the pelicans eat it. This one looks like the pelicans got it. Its head is all nice. And what does this ornament mean? If we put a dot, now I don't want to confuse this with the dotted cobordisms, which you might be familiar with. This dot is going to mean just apply what's called a curtain with a handle on it. So we're just going to do a little genus 1 cobordism. Okay. So that's what you apply here. Okay. So it's okay since we started a couple minutes late. I just want to do one calculation. Or sorry, let me do one more. Do I actually have time to do it? Okay, I will. So I'm going to do one calculation, but first I want to pause. I've only drawn for one of the sort of signed R1s and its inverse. But in general, to interpret these, we now know what they should look like. For example, this, if I sort of turn it to the side, is going to look like that. We're going to apply a cap to this, and then just take the identity on that. Here, a little more complicated, but you could construct it. So the we'll see the birth of a component, and then a genus on it. Well, it's the identity over here, and plus something which is the birth of a component, but then a saddle to a sheet over here. And so hopefully this is enough information to figure out how to read the tables. In the exercises, there's two tables listed describing R1 and R2 moves. So there's questions about how to interpret those. Hopefully Yikai can help. But what I want to quickly close with is suggesting an informal exercise and a recommended calculation. So if these are supposed to be R1 and R1 inverse, then if you compose them you should be getting a map which is the identity. At least maybe a plus or minus one or something. And so you can ask, well, if I actually compose the associated cobordisms in D2 cross the interval, then do I just get a sheet, just a straight product? Answer is going to be no. You can tell it's going to have genus because it includes this dotted piece. And so how do we know, how do we know that that's inducing the correct map? Well, we know that if we cut it up, what you'll see is that there's a closed torus sitting inside of your cobordism. And so you can take that and remove it at the cost of multiplying by 2. So in general, Barnatonis will give you a sort of a language for manipulating these cobordisms, but in such a way that the induced map is the same. And that's actually what essentially goes into the proof of Reidemeister invariance. But the final thing I just want to recommend is from here, it's easy enough to get the sort of first proof of concept that KH can distinguish slice disk. So you want to consider the mirror of 946 is the pretzel knot -3, 3, -3. And there's two ways you could, bless you, two natural ways you could turn this into or witness this as a slice knot. If you perform a band here, then you can see that you're going to get a column of R1s to untwist. And then this, you can show that the remaining is just a 2-component unlink. It takes pull it apart with some Reidemeister 2 moves. Or you could do the same thing by symmetry on the other side. These are distinguished by where they map this element I'll call phi, which is, let's say, there's going to be 2 of them, but I'll just draw one of them. So that will be with X labels on everything. So if we're looking, this is a 0 resolution, 0 resolution, 0 resolution, and then 0 resolution, 0 resolution, 0 resolution, 1 resolution, 1 resolution, 1 resolution. So one of these disks, the cobordism map will kill it. Maybe I'll just show you. We can tell right off the bat that the cobordism map associated to this red band, when we do that pinch, what's that going to do to this? It's going to be a merge map between this component and this component. Those are both X labeled, and merge of X tensor X is 0. So I haven't convinced you, I haven't told you why this is a cycle, but you could check that it is. And then we know that this is going to die under the red disk. And the question is, can you show that it is non-trivial under the blue one? Okay, so let me wrap up there. Sorry for going over. Yeah.
In this case, they're both you establish topological isotopy of the disks by do they both disk complements of fundamental group C?
No, they do not. So yeah, so just repeat the question. That was the first one was if these disk complements of fundamental group Z, because thinking about sort of topological isotopy. The answer is no. But I'll let you finish the question if there's more to it.
No, that's it.
Yeah. So then let me finish the add to the question. So it turns out that these disks aren't even topologically isotopic. I can't resist really quickly. I would tell this anecdote. These disks also can be realized as Lagrangian surfaces in the 4-ball. And there's paper, I think it's in a paper by Tobias. Distinguish those disks up to like Hamiltonian isotopy, nice families of symplectomorphisms. And I heard some topologists sort of snickering and being like, they're not even homotopy equivalent about boundary. the way you can distinguish these surfaces is by looking at one way you can do it is by looking at the map from the not complements fundamental group to the disk complements fundamental group. And what you can show is these loops clearly in the blue disk, gamma is going to be null homotopic in the formal because it found the disk which is going to have a Rubin intersection with this, and so they're going to be just additional embedded in the four ball. So this is null homotopic in the disk complement for the blue one, but it's going to be non-trivial in the disk complements fundamental group for the red disk. And so anyway, so some pathologists were sort of snickering that why would you use symplectic or techniques to prove this? And I told this to or Mohammed Abasayed was there, and he was completely unaffected and was like, yeah, but even if they were topologically isotopic, they still wouldn't be Hamiltonian isotopic, which is, like I said, a very safe statement to say, but there's real wisdom to that, which is the proof that they're not isotopic as Lagrangian surfaces generalizes to lots of surfaces that are not so obviously topologically distinct. And indeed, the Kavanov argument here that distinguishes these, sure, even though you didn't need Kavanov homology, the exact same strategy is going to successfully distinguish exotically knotted disks. And so there's some sort of topological insight for looking at, if I know why, like, what the topological difference is between two different disks, that is, where are the band moves, we can often use that to help guide the construction of some elements that we know will behave nicely. So here, the fact that this loop is going to be associated to this disk is part of what guides the choice of, we want this move to merge two different smoothings. So anyway, there's a bit of sort of a long-winded answer, but the point is, even though they are topologically distinct, the way that we're proving, the reason that they're topologically distinct helps us also guide the Kavanov proof.
I think I just misunderstood that. I thought this was an example of an exotic pair.
No, just two different slice disks. Just two different slice disks of the isotopic bell boundary. Cool. Yeah. I should say on the homework, the last problem, if one chooses to do it, will distinguish them exotically knotted. There won't be slice disks, there'll be separate surfaces, but yeah, other questions?
When you say like the blue slice disk, it's not the band in the picture. You use the band and then you cap off the two knots. Is that what you mean?
Right. So so let me state back something I didn't ask if that was a question. If we do this band move, that has the effect of we pass down into the movie and we see this. This is a two-component unlink. If we just need to undo some right and Western moves. Was that essentially the question?
Yeah.
Okay, great. Again, so I recommend people try to do this calculation. You'll just need to use these readings of the ornaments and the maps we defined. Yeah, any other questions?
I think I'm kind of confused about the surfaces in 4D part. Like I understand, okay, we have a link diagram. We make this cube of resolutions. We get some complex. We have these maps. And then there's like a nice way to interpret these maps as cobordisms. But like, but then what? Like,
How you put it together?
yeah, like what is the statement? Like what's the conclusion?
Well, so okay, if I'm allowed to really briefly, I don't know if it would help. So let's say we proceeded with what we're describing. If we're going to sort of consider the surface now, which starts with resolving that blue band, then we're going to see a movie where the next slide is this. And if we want to track what happens under the cobordism map from homology of, I'll call this K. So that's going to be, the next thing we some two-component unlink, but then we're going to cap it with two minima. And so what we want to do is consider where this goes, but we need to write down our movie. And so in our movie, we're going to see like Reidemeister 1. Well, sorry, what I should have said is the first step in this movie, because we have the saddle, is going to send this to carefully. Something like that. But we can check this splits this into an X and an X. X, X, X.
Okay, so maybe my question is
Yeah.
more basic, like when you write KHK, what do you mean, like what is that?
Oh, so everything I'm writing, are explicit chain elements, but in this case, they're also cycles, and so they represent genuine homology classes.
When you write KHK, you mean it's like, it's like the homology.
Yeah, exactly. Sorry, it's the homology of the chain complex we've been looking at. Yeah, sorry about that.
Yeah, see, so then. So you're saying cobordism induce mass between the.
Yeah, sorry, I said, I left this implicit. I should have said it more explicitly. These maps that we're defining between labeled smoothings, they naturally give us chain maps now. And one can check that they are, and this is another sort of good informal exercise, we can check that they're actually, I guess I already accidentally used the word, okay, they're chain maps. So they're maps, these maps on the chain level are chain maps. And so they're going to induce maps on homology. Yeah, sorry, thank you. Yeah, I forgot to sort of put that connective tissue into the explanation. Yeah, but the point is if we apply all those now back at the chain level, which we can do bit by bit, we'll see that this on the chain level sends phi to over z to plus or minus 1. I mean, actually also over z 2 to 1, but over z plus or minus 1. Yeah, thanks.
Thank you.
We're gonna just let me keep going with questions. I'm happy to. There's one more question otherwise. Okay, I'm not communicating yet. Yeah, please.
Oh, one quick one.
Yeah.
Do there exist like distinct surfaces that give you the same maps on the homology, or is that enough to distinguish a surface?
No, so these are not complete invariants. The simplest example I could give you is if you cheat and use coefficients, you can sort of miss some surfaces. So there's two slices naturally bounded by the stevedore knot, sort of two standard size disks. Those induce distinct maps over Z, but not over Z mod 2. So if you only were careful Z mod 2, you would never be able to see the difference. But maybe those aren't the best examples. The best examples that I know of are an infinite family of genus 1 surfaces produced by Gomf by, I think the knot's like 12,141 or something like that, but one can look it up. But the point is these differ by this type of infinite twist. The knot has it has a spot, maybe this isn't super essential. It has a spot where you can put in like a negative crossing box, and then there's some stuff, and then a positive crossing box and some stuff. And at the level of the knot, there's actually a kind of funky isotopy that cancels these crossings. But if you do like a band move between them, then the effect on the movie is to sort of wind this band around and around and around. And you can show that homology does not see the difference between those maps. In the language of what's on the exercises today, it turns out that all of those surfaces can be realized as quasi-positive surfaces, and the bigrading in which the map would have to be supported is generated by what's called Pomonowski's invariant, and quasi-positive surfaces just all act the same on that one invariant. So we know that there's sort of not rich enough structure to see the difference between them. Yeah, thanks. Sorry, I found a way to give a very long answer to a very short question. Surprise, surprise.